In 1995, a small team of engineers at Israel Military Industries gathered in a development workshop outside Tel Aviv with an unusual directive: design a rifle that would be 30% shorter than the M16 while maintaining identical barrel length and accuracy. The project had no formal name yet, only an internal designation and a thick folder of operational requirements compiled from field reports spanning 3 decades of service. The lead mechanical engineer, examining the specifications, understood immediately that conventional architecture couldn't satisfy these contradictory demands. The mathematics were unforgiving. You couldn't simply remove material from an existing design and expect it to function. What they needed was a fundamental re-architecture of how rifle components related to each other spatially. The workshop contained prototypes from previous attempts at compact rifles, each representing a different compromise. Shortened barrels meant reduced velocity. Folding stocks introduced mechanical complexity and reliability concerns. Specialized submachine gun calibers limited range and penetration. The requirement wasn't asking for a specialized tool for niche applications. It demanded a universal service rifle that happened to be dramatically shorter. One engineer sketched a rough diagram on the whiteboard. What if they simply moved everything backward? The magazine, the action, the entire operating system shifted behind the trigger group. It wasn't a novel concept. Bullpup configurations had existed since the 1940s, but previous implementations had consistently encountered the same obstacle. Personnel trained on conventional rifles found them awkward and unnatural. The team spent the first month not designing mechanisms, but studying the precise ways users interacted with their equipment. They filmed hundreds of hours of training exercises, noting hand positions, reload sequences, maintenance procedures, sight picture acquisition. What became clear was that the objections to bullpup designs weren't about capability. Most performed reliably in testing, but about deviation from ingrained muscle memory. The magazine release in an unfamiliar location. The balance point shifted toward the shooter's shoulder, the proximity of the ejection port to the face during left-handed operation. Each difference compounded into a tool that felt alien even when it functioned correctly. By late 1996, the project team had crystallized around a key insight. They couldn't change how personnel had been trained for generations, so their design would need to minimize the cognitive distance between conventional and bullpup architectures. The trigger would need to feel crisp despite the long transfer bar. The controls would need to be immediately intuitive. The maintenance procedures would need to follow logical patterns familiar from existing equipment. Most critically, the ejection system would need to accommodate both right and left-handed users without requiring them to accept hot brass ejecting across their field of vision. This last requirement seemed impossible until someone suggested they simply make the ejection direction changeable. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far, and stay with us for the next chapter. The challenge facing Zalman Shebs, the project's chief designer, wasn't purely technical, it was temporal. By 1998, the IDF had already begun preliminary discussions about replacing the M16 variants and Galil rifles that formed the bulk of their inventory. Competing proposals included importing proven foreign designs or developing an entirely new conventional layout rifle. The Bullpup project, still officially experimental, risked becoming irrelevant before proving its concept. Shebs understood that they couldn't simply build a functional prototype. They needed to build something so demonstrably superior that it would overcome institutional resistance to unconventional designs. The engineering team faced a specific dilemma with the fire control system. In a conventional rifle, the trigger mechanism sits immediately adjacent to the sear and hammer. In a bullpup, that trigger must actuate components 15 to 20 centimeters rearward, requiring some form of transfer mechanism. Previous designs had used linkage bars, long metal rods connecting the trigger to the fire control group. But these consistently produced spongy, imprecise trigger pulls that experienced users found unacceptable. The military specification demanded a trigger brake weight between 2.9 and 3.6 kilograms with minimal creep, standards derived from decades of marksmanship training doctrine. A poor trigger would jeopardize the entire project regardless of other merits. The solution emerged from an unexpected source. One of the younger engineers, examining a trigger mechanism from a different system entirely, noticed how a carefully designed cam system could convert linear motion into rotational force with minimal friction loss. He applied to the Tavor. This meant replacing the simple linkage bar with a more sophisticated transfer mechanism incorporating multiple pivot points and spring return systems. The resulting trigger wasn't just adequate. Testing showed it matched or exceeded the feel of the M16's direct trigger system. This single component took 8 months to refine, but it removed what had been considered a fundamental limitation of bullpup architecture. Simultaneously, the team grappled with the gas system. The Tavor would use a long-stroke gas piston design proven in previous local equipment, but integrating it into the bullpup layout presented unique challenges. The gas port on the barrel needed to sit at a specific distance from the chamber to provide proper dwell time, the period during which gas pressure drives the piston. But in the compressed bullpup architecture, that meant the gas tube and piston assembly had to route through a space already occupied by the user's shoulder and stock. The solution required careful three-dimensional modeling to find a path that didn't interfere with structural components while maintaining proper alignment. The piston itself was redesigned with a subtle taper that allowed it to pass by the bolt carrier at a slight angle, saving precious millimeters of space. By 1999, functional prototypes existed, but they revealed a new problem. The compact dimensions created excessive muzzle blast for users. The short overall length meant the muzzle sat closer to the user's head than in conventional rifles, and the acoustic pressure became uncomfortable during extended sessions. This wasn't merely a comfort issue. Prolonged exposure could cause hearing issues even with protection. The team developed a compensator design that redirected blast pressure forward and slightly upward, mitigating the effect without significantly increasing overall length. Each solution created new considerations, a cascade of interdependent engineering decisions. Understanding the Tavor's mechanical operation requires visualizing its gas system architecture. When a cartridge is activated, high-pressure gas follows the projectile down the barrel. At a precisely calculated distance from the chamber, approximately 20 centimeters in the Tavor, a small port in the barrel allows some of that gas to escape into a tube that runs parallel to the barrel. This gas impacts a long piston rod, driving it rearward with considerable force. The piston doesn't directly contact the bolt. Instead, it strikes the bolt carrier, a separate component that houses the rotating bolt. The bolt itself contains multiple locking lugs, precisely machined protrusions that engage with matching recesses in the barrel extension. When locked, these lugs prevent the bolt from moving rearward, containing the pressure within the chamber. The bolt carrier's rearward motion initiates the unlocking sequence. A carefully designed cam path inside the carrier engages a pin on the bolt, forcing it to rotate approximately 20 degrees as the carrier moves backward. This rotation disengages the locking lugs, allowing the bolt and carrier to move rearward together as a unit. As this assembly travels rearward, several events occur in precise sequence. The extractor, a small claw-shaped component on the bolt face, maintains its grip on the cartridge case rim, pulling the empty case from the chamber. The ejector, a spring-loaded pin, pushes against the case head from the opposite side. When the case clears the ejection port, the ejector's force causes it to flip outward and away from the rifle. The recoil spring, compressed during this rearward motion, stores energy for the return stroke. This entire sequence, unlocking, extraction, ejection, occurs in approximately 10 milliseconds. The return stroke demonstrates equally precise engineering. As the recoil spring expands, it drives the bolt carrier forward. If a fresh cartridge sits in the magazine, the bolt face contacts its base and strips it from the magazine, pushing it forward into the chamber. The cartridge's casehead slides up the bolt face, riding over the extractor claw until it snaps into the extractor groove with a subtle click. Continued forward motion chambers the round fully, and the cam path reverses its earlier action, rotating the bolt to lock the lugs into battery. The piston, having been driven forward by its own return spring, sits ready for the next cycle. The trigger reset has occurred during this stroke, prepared for the next activation. What makes this system notably reliable is its tolerance for adverse conditions. The long-stroke piston design means the bolt carrier gains significant momentum during its rearward travel. This momentum helps overcome friction from sand, dust, or carbon buildup, contaminants that cause issues in more delicate systems. The large bolt lugs distribute locking forces over substantial surface area, reducing wear and allowing extended service life. The extraction system, with its robust extractor and positive ejection, functions reliably even with cases that have begun to corrode or deform. The Tavor's modular barrel system deserves particular attention. The barrel doesn't thread directly into the receiver, as in many designs. Instead, it mates with a barrel extension that remains with the bolt. This separation allows the barrel to be removed by releasing a single locking lever near the gas block, requiring no tools and maintaining headspace automatically. For logistics, this meant damaged barrels could be replaced at the unit level without specialized intervention. For different caliber conversions, it enabled relatively simple reconfiguration. The engineering elegance lay not in complex mechanisms, but in the careful arrangement of simple components to enable field-level modularity. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The initial field trials in 2001 revealed problems that static range testing hadn't predicted. The Tavor functioned reliably in controlled environments, but operational conditions introduced variables that challenged the design assumptions. Sand intrusion through the ejection port proved particularly troublesome. In a conventional rifle, the ejection port sits above the user's grip, relatively protected from environmental contamination. In the Tavor's bullpup configuration, that port sat much closer to the ground when the rifle was set down or during low crawling maneuvers. Fine dust accumulated in the action during extended exercises, gradually increasing friction until the bolt carrier's travel became noticeably slower. The engineering team responded with a redesigned dust cover system that sealed the ejection port more completely when closed. But this created a secondary problem. Users in high-stress situations sometimes operated the equipment with the dust cover closed, causing malfunctions. The solution required rethinking the dust cover's mechanical advantage. They designed it so that if the bolt attempted to cycle with the cover closed, the force would automatically snap the cover open rather than jamming the action. This fail-safe approach transformed a potential liability into a robust feature, though it required precision manufacturing to ensure the cover's retention spring provided exactly the right resistance. Testing also exposed issues with the magazine catch placement. In a conventional rifle, the magazine release sits where the index finger naturally rests. The Tavor, maintaining this conventional positioning, placed the catch just forward of the trigger guard. But the bullpup configuration meant magazines seated much closer to the user's body, and the release mechanism required a different angle of force to disengage. Some personnel reported difficulty achieving reliable magazine changes, particularly when wearing gloves or under stress. The catch was redesigned with a larger engagement surface and modified spring rates, a seemingly trivial change that required months of testing to optimize. The ambidextrous ejection system underwent the most significant revision. Early prototypes required nearly complete disassembly to change ejection direction, removing the butt plate, extracting the fire control group, and accessing the bolt. This defeated the purpose of field adaptability. Engineers spent considerable effort developing a system where only the bolt and ejection port cover needed replacement, components that could be changed in under 2 minutes with no tools. The challenge lay in maintaining consistent headspace, the critical distance between the bolt face and barrel across different bolt configurations. This required extraordinarily tight manufacturing tolerances on both bolt and barrel extension, increasing production costs but ensuring reliability. By 2003, the refined design had addressed the major field issues. The IDF began limited operational trials with specialized units gathering data on long-term reliability and maintenance requirements. These trials revealed that personnel adapted to the bullpup layout more quickly than anticipated, largely because the Tavor's control placement mimicked conventional rifles wherever possible. The reduced length proved genuinely advantageous in vehicle operations and urban environments. Accuracy remained consistent with full-length rifles, validating the fundamental premise that barrel length, not overall length, determined projectile performance. The modular ejection system's true significance emerged not from internal requirements, but from export market realities. As other nations expressed interest in the Tavor, IWI discovered that different countries had different preferences for ejection direction based on their existing training doctrines. Some organizations trained all personnel for right-hand operation regardless of natural dominance. Others accommodated left-handed users with specialized instruction. A few had no established doctrine for bullpup equipment and wanted the flexibility to develop training programs based on field experience. Traditional manufacturing would have required producing entirely separate models for right and left ejection, each with dedicated production tooling, parts inventory, and maintenance documentation. The costs and complexity would have made small quantity exports economically unfeasible. The Tavor's approach, building a single-base rifle with interchangeable ejection components, transformed the economics entirely. A single production line could supply diverse markets. A single logistics system could support multiple configurations. Customers could purchase right ejection units initially, then acquire left ejection conversion kits as training doctrine evolved, without making existing equipment obsolete. What made this possible was a subtle but fundamental design decision in how the bolt, barrel extension, and receiver interface with each other. In most rifles, the bolt is a highly specific component machined to work with one particular barrel extension, and both are fitted to a specific receiver. Interchangeability requires such tight tolerances that it becomes impractical. The Tavor's designers approached this differently. They established a precise datum surface, a carefully machined reference plane in the receiver, that served as the single critical measurement point. Both the right ejection and left ejection bolts referenced this datum identically, the barrel extension locked to the receiver in a way that ensured consistent positioning relative to this datum, regardless of which bolt configuration was installed. This meant that headspace, the critical dimension affecting both safety and reliability, remained constant across configurations. A technician could verify headspace on one configuration and be confident it would remain correct when converted to the opposite ejection direction. The engineering sophistication lay in the careful tolerance stacking analysis and the design of interlocking components that maintained relationships in three-dimensional space while allowing modular assembly. It wasn't a revolutionary mechanism. It was meticulous application of fundamental geometric principles. The revelation extended beyond ejection direction. The same modular architecture facilitated caliber conversions. By changing the barrel, bolt and magazine while maintaining the same receiver and fire control group, the Tavor could transform from 5.56mm NATO to 9mm or to 5.45 VAGs 39mm for different markets. Each conversion maintained reliability because the fundamental action principles remained constant. The gas system's adjustable settings accommodated different pressure curves. The magazine well accepted different patterns through interchangeable adapters. This modularity wasn't merely convenient, it represented a fundamentally different approach to service rifle design. Previous equipment typically served its intended role for decades with minimal modification. The Tavor suggested a future where equipment evolved through component updates rather than complete replacement. An organization could adopt the platform in one caliber, then shift to different standards as doctrine or logistical considerations changed, without retraining personnel on entirely new systems. The investment in training and doctrine development remained valid across hardware evolution. The Tavor's formal adoption by the IDF in 2009 marked not an ending, but a transition point in ongoing evolution. Entities rarely adopt truly revolutionary systems. They adopt refined implementations of proven concepts that solve specific operational problems. The Tavor succeeded because it addressed real tactical needs, compactness without sacrificing capability, while minimizing the adaptation burden on personnel and logistics systems. Its modular architecture allowed it to remain relevant as requirements evolved, a capability that proved more valuable than initial specifications suggested. The engineering lessons extended beyond the tool itself. The development process demonstrated that solving user interface problems often requires more sophisticated engineering than solving purely mechanical challenges. Creating a trigger that felt natural across a 15-centimeter transfer distance demanded more innovation than the basic gas operation system. Enabling tool-free barrel changes required more careful tolerance analysis than ensuring the barrel could contain internal pressures. The difficult engineering often hides in the details that users never consciously notice. The subtle contours that guide hand placement, the precise spring rates that govern control feel, the geometric relationships that allow components to be interchangeable while maintaining critical alignments. Modern organizations increasingly recognize that equipment serves within broader systems, logistics, training, doctrine, and the industrial base. A rifle might represent superior technical performance, yet fail if it requires specialized maintenance equipment, or if it depends on components from a single supplier, or if it demands rewriting decades of training doctrine. The Tavor succeeded partly through engineering quality, but equally through attention to these system-level considerations. Its modular architecture aligned with contemporary preferences for platform adaptability. Its manufacturing approach balanced precision with producibility. Its maintenance philosophy matched realistic field capabilities rather than ideal workshop environments. The legacy appears in subsequent designs from multiple manufacturers, many incorporating modular approaches to components traditionally considered fixed. Barrels, bolts, and caliber conversions have become expected features rather than unusual capabilities. This shift reflects changing industrial and operational realities. Smaller production runs for diverse markets, longer service lives requiring midlife updates, and doctrinal evolution within a platform's operational lifespan. The Tavor didn't invent these concepts, but its successful implementation demonstrated their practical viability for service rifles, influencing how other designers approached similar problems. Engineering history tends to remember dramatic innovations, the first of something, the largest, the fastest. The Tavor represents a different kind of achievement, the careful refinement of existing concepts to solve practical problems within real constraints. Its significance lies not in revolutionary mechanisms, but in the systematic attention to how mechanisms interface with users, manufacturing systems, and logistical networks. This approach, engineering as integration rather than invention, increasingly defines successful modern systems. The tools that serve longest and most effectively aren't necessarily those with the most innovative mechanisms, but those designed with an honest understanding of how they'll actually be used, maintained, and evolved over decades of service. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching. Would you like me to translate another technical script or assist with further naturalization of this text?